Video we're going through the practice test for further trigonometry, and we'll be using the Casio calculator in this video. So before we make a start, I just want to talk about the performance standards here. This one's just can you do the maths and then can you make models. Then the next one's going to be using technology, so that's really those calculator questions, interpreting your results and making conjectures. So be aware there'll be quite a few conjectures that we'll be making and proving. Okay, so question 1 is this question about the bakery in Cleve, and it's about when the bakery should be open. So we're open from 7 a.m. to 5 p.m. and it's sort of modeling how many people are in that bakery at any given time. So we're going to go to our graph, and anytime you see a very wordy question like this, more often than not, you're actually just doing it on your graphing calculator. So we're going to put that function in 10 plus 5 cos brackets pi over 2 brackets x take 1. X instead of t because we're in calculator land here. Now Casios have a really bad habit of messing up the equation like that. So pi over 2 brackets x take 1. Yeah, I want to make sure I bracketed the entire thing there. Alright, there we go. That's a lot better. So we're going to hit draw and we'll see what it looks like. Looks like absolute trash because we haven't set up our window. So we're going to go V window. It says t goes from 0 to 10. So that's exactly what we'll do, 0 to 10. And if we look at our equation, it's got a d value of 10 and an a value of 5. So it should go up to 15. 0 to 15. If you're not comfortable doing that, use trial and error, thinking how many people might be in a bakery. In this town, it happens that no more than 15 people will ever be in this bakery. I'm just going to set my window to be that tiny bit higher than 15 just so we can see it. Maybe I'll set it to 20. Alright, there we go. So we're going to be drawing our graph here. And then what I recommend is you sort of just go across. Make sure you're going all the way up to 10 using a ruler, of course. And that's your t. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then your p values are going to go up here. And we have to go up to at least 15. So I'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then what I would do is be using the trace option to sort of figure out what all your values that you want are. So at x equals 0, we're starting at 10. I'll just do a different color for that. And then we're going to go across. So maybe shift trace x equals trace x equals 1. It looks like we're hitting that maximum. So at 1, we're hitting 15. And I'd probably even label that first bit. Shift trace. And then at 2, we're back to 10, and it looks like it's going to sort of follow this pattern as it goes down. So at 3, it's going to go down to 5 and then back up, and then hitting a maximum again there at t equals 5, coming back down 6, 7, 8, hitting a maximum again at 9 and 10. And that's sort of what our graph's going to look like. Then all you need to do is connect up the dots. Try and make sure your graph looks pretty smooth there. And we don't need an arrow on the end because the bakery actually does close when t equals 10, so it doesn't keep going. We'll label our equation with the appropriate function there. So that's going to be p of t equals 10 plus 5 cos of pi over 2, t take 1. All right, there we go. How many people are in the bakery when it opens at 7 a.m? Well, we worked that out before. So at t equals 0, there are 10 people. And then we want to know how many people are in the bakery at 2 p.m. So one thing that could help is if we have t values and then the actual time. So when t equals 0, we're at 7 a.m. When t equals 1, we're at 8 a.m. When t equals 2, we're at 9 a.m. When t equals 3, we're at 10 a.m. When t equals 4, we're at 11 a.m. t equals 5, we're at 12 p.m. t equals 6, we're at 1 p.m. t equals 7, we're at 2 p.m., which is that time that we wanted. And it keeps going up until t equals 10, which is 5 p.m., and that's also when it said the bakery closes. So t equals 7 is what we want here, and all we need to do is go shift trace 7, and then that's going to tell us there are 5 people. And then we want our maximums. So there are 3 rushes of the bakery. It has the largest number of people in it. Find these 3 rushes and sort of interpret your answer. So we're going to go max here. The first one is at 115. Next maximum is at 515. And then the next one ends up being at 915 if you click across to that one. There we go. So we can say the max number of people is 15 at, and then we'll get those times. So the times correspond to t equals 1, t equals 5, and t equals 9. So this is 8 a.m. This is 12 p.m. And this is 4 p.m. And the next question sort of asks you why. So the 8 a.m. one is probably people getting breakfast before work. That's probably what's happening there. And then 12 p.m. is probably people getting lunch. And then the 4 p.m. might be people finishing probably school most likely, or work, and they are going to bakery. All right, Nigel works the morning shift from 5 a.m. to 1 p.m. at the bakery, and he needs to take a break, but only if there's less than 7 people in the shop. So this is going to be shift, shift G solve, go across to xcal when y equals 7. So we can see that happens at 2.409 is when it goes under 7, and then it's going to stay under 7 people until we hit 3.590. Now, there are a few more times that he could, in theory, take his break, like, for example, here, 6.409. But if you look at t equals 6, that's 1 p.m. And that's exactly when Nigel finishes his shift. So, yeah, that's not really going to work for us, is it? So it's a bit after 1 p.m. that it dips below that. So he has to take his break in this first little dip here. Because if he tries to break it in the second dip, well, he's already finished his shift at that point. So 2 corresponds to 9 a.m. And if we want to convert that 0.409, which I actually probably should have rounded to 410, if we want to convert that to minutes, all we have to do is go back into your normal mode and go 0.410 times 60 to get it into minutes. There we go, 24. So 925 if I round that to 0.590. So 0.590 times 60 is going to be 35.4. So to 1035. And then that is when he can break. That's when there are less than 7 people in the shop. So yes, he can get a 30-minute break. In fact, by quite a lot. He could even get a 70-minute break if he wanted. All right, so next we're going to solve these equations in exact form. Remember, angles are in radians. So there are ways to sort of cheese this and get an idea of what to expect. So it's asking for 2 sine of x equals minus root 3. So you're not at all supposed to do this on your calculator, but you can just have a cheeky look and see what you're expecting. So 2 sine of x should equal minus root 3. So we'll put all that in. We'll draw it. But really importantly, before we draw it, I want to set up my window to only go from 0 to 4 pi. And then y can maybe go from minus 5 to 5 or something like that. So if I actually have a look at this graph, you can see that this is happening 1, 2, 3, 4 times. I'm expecting 4 solutions. So let's do this by hand because it wants the exact values. 2 sine of x equals minus root 3. We're first going to arrange to sine of x equals minus root 3 over 2. And then I'm looking for all the x's that will give me minus root 3 over 2. So that's where you need your formula sheet for this test. And we're looking for minus root 3 over 2 as our sine value. That's going to happen at 4 pi over 3 and also 5 pi over 3. So x is going to be 4 pi over 3 and 5 pi over 3. And then we need to keep adding on multiples of 2 pi to get any more angles. So plussing on 2 pi there, which is the same as adding on 6 pi over 3, is going to give us up to 10 pi over 3 for our next answer. And then if we do the same thing there, we're going to get 11 pi over 3. Now if we kept going, 10 pi over 3 plus gives us 16 pi over 3. But that is too big because 16 pi over 3 is a lot bigger than 4 pi. 4 pi is like 12 pi over 3, so you can see 16 is too big. All right, so those are our 4 angles that we get, and that's sort of what we expect. In theory, if I go shift, trace, and I type in 5 pi over 3, that should put it on that second intersection point that I saw there, which it does. Okay, next we got 2 cos 4x take 1 equals 0. First thing you do is arrange it. So 2 cos of 4x equals 1, and then cos of 4x equals a half. So that's going to be that 4x equals, and we got to figure out all the cos values which give us a half. Cos is a half at pi over 3 and 5 pi over 3. Again, we're going to keep adding on multiples of 2 pi, so our next one is 7 pi over 3, and then 11 pi over 3, and then 13 pi over 3, and then 17 pi over 3, and you can keep going if you want, like 19 pi over 3, but we'll see this is going to get too big. So if we want to go here, we're then going to divide by 4 to get x, and we need to divide everything by 4. So we're going to get pi over 12 for our first one, because like when you're dividing by 4, 4 ends up on the bottom, 3 times 4 is 12, so we're going to get 5 pi over 12, 7 pi over 12, 11 pi over 12, 13 pi over 12. But you can see that pi is like, well, it's 12 pi over 12. So this one is too big. So again, we're going to get 4 answers here. So these are our answers. These are our x values. All right. So that's how we do that question there. Next, we got question 3. So it's a graphing question. Now, in this question, I've given you the actual values as well, and that's so that you can be really precise. So we're looking at temperature in Whyalla, and really in particular, you're looking at this red line that's sort of coming across like that there. So that's the graph we're going to be modeling. So first thing we're going to do is give the period of the graph. It is 12 months, and that should be sort of like real world reasoning there as well, because the temperature does repeat every year. And then we're going to put first here, we don't need to put this explicitly, but it will help a lot. We're going to get our min temperature and our max temperature. So min seems to happen in July there, which is 16.9 degrees Celsius. And the max appears to happen in January, which is 29.2 degrees Celsius. And then we need to get our A, B, C, and D values. All right, so our A, B, C, and D values. So what we need to do is sort of look at going back to our normal calculator mode. So 29.2 take 16.9 will give us that number, 12.3. And what I've just worked out is sort of like the total height of the red line. And we need to divide it by 2 to get the amplitude. So 12.3 divided by 2 is what we'll do, which is 6.15. Next, easiest one is your D value. So I want to take the minimum, 16.9. And I already know halfway up is 6.15, so I'm going to get 6.15, and that gives me 23.05. My D value, which you can hopefully see that 23.05 is there. That is roughly like halfway in between where the graph is. So that's what we're looking for there. Also, it's the number exactly in the middle of 16.9 and 29.2. Now, B value is going to be 2 pi over the period, or pi over 6 if you'd like. Now, notice that the maximum does actually happen at t equals 0, which is January. So we can actually model this as a cosine function and just have no translation, because we know a cosine function tends to start at the top. So temperature, big T for temperature, is going to be 6.15 cos of pi over 6. T take nothing, so I'll just leave that as T. Plus our D value, which is 23.05. Now, if you had something a little bit different, as long as you still get the same graph, you will get the same answer. So for example, you could have modeled this with a sine function and a different C value, for example. Or if your numbers were slightly different, that's okay. But I really would like, and the super A-level answers would be using these numbers here, because the 16.9 in July sort of corresponds to like that 16.9 there. So understanding the relationship between the graph and the numbers is very important. Your model repeats the same for all future years, and we need to explain whether this is possible in the real world. Or reasonable? No, not really, because basically because of climate change, it might get warmer. Also, not all years are the same. So it's just like this thing that happens every 5 or 6 years. There's sometimes this really weird year temperature-wise. I think, if I'm not mistaken, 2022 in Wyler was particularly cold. So you can't expect it to repeat exactly the same every single year. That's not realistic. But it will be roughly the same. All right, next one I'm doing is cot squared of pi of 3. So that's exactly what we're going to do here. Cot is 1 over 10, and we need to make sure we're in radians. Very important because they're talking about angles in radians. Just make sure you're there, which we are. So we're going to be doing basically 1 over 10 pi over 3. That is our value there, and we're going to be squaring that entire thing because we're doing cot squared. So that is a third, and if we just do that approximately, it's 0.333. And then the next one is cosec squared of pi over 3. So we're going to be doing 1 over sine of pi over 3. Pi over 3, close the brackets, and then we're going to be squaring that. So we get 4/3, or if you want, it's 1.333. So we'll put those straight in our table. Now, if you know how I write tests, you might be able to sense that a conjecture is coming up very soon. And that's because you can see this table where we're trying to spot a pattern here. Now, one thing that I really want you to do is actually look at this 1.894 number, actually calculate cot squared of pi over 5, and make sure you can replicate that you get that number as well. Now, the reason I actually put that in the table is so that you can sort of check that you're doing the process right by checking, hey, I do get the same number as what's in the table there. And if you do cosec squared, you should get 2.894 there too. All right, so next we're going to go 1 over 10 of pi over 7. So that is cot of pi over 7 that I've just worked out. Pi over 7. Close your brackets and you will square that. And that's going to give you 4.312. Then we're going to get cosec squared of that same angle, pi over 7. So 1 over sine of brackets pi over 7. Do that and square it. You're going to be getting 5.312. And then the next one, the angle is literally just 2 radians. So 1 over 10 of 2 squared. So 0.209. And then we're going to be going like 1 over sine of 2 squared, which is 1.209. Now, hopefully you can spot the pattern at this point. If you look at that right column, they're all one more than the left column. So cot squared of theta is the left column. If I add 1 to that, I should get what's on the right column, which is cosec squared of theta. That's my conjecture for all theta in R, we could say. Preview conjecture, so we want to start from this identity, which I will do. Sine squared of theta plus cos squared of theta equals 1. Now, this is really easy if you know the trick. So the trick is that we're going to be dividing by something on both sides. All right, so what are we going to divide by? Well, we've got a 1 here, but on the right side of our conjecture, we have cosec squared, and we know that cosec is like 1 over sine. So maybe I should be dividing by sine squared of theta to get what I need. So let's do exactly that. What we're going to get is sine squared of theta plus cos squared of theta equals 1. And we're going to be dividing each of those terms by sine squared of theta, and we'll see if that works. All right, so let's see. First term, sine squared over sine squared is just, well, 1. Plus, now cos over sine is like upside down tan, and we have a special name for that. It's cot. And then 1 over sine squared is cosec squared theta. It's almost what we look like in our conjecture, except that we had cot squared first. So cot squared of theta plus 1 equals cosec squared theta. So if you want to be really clear about proving this conjecture, you can be like dividing by sine squared of theta on both sides. Something like that. Okay. There we go, as required. So that's our conjecture proven. Next we have question 5. So find the exact value of sec pi over 6. So we could try and use our calculator, but we want the exact value. So we probably should be using our unit circle here. So this is the same thing as saying 1 over cos of pi over 6. And we need to know what cos of pi over 6 is. Pi over 6, cos is root 3 over 2. So that is going to be 1 over root 3 over 2. which is just 2 over root 3. Now, if you're not sure about that, so 1 divided by root 3 over 2 is 1 times, and then you got to flip it. So 2 over root 3, which does just simplify down to 2 over root 3 for you. Right, this next one is write this expression using a single trig function. So they just want like sine of something or cos of something or sec of something. Now this one looks like our double angle formula there. So cos and sine. So it looks like the cos one. Since it's a plus, we've got to flip it to a minus. So I'm going to get cos of 40 minus 10, which is going to give me cos of 30. Now, one way you can actually double check this is with your calculator. So make sure you're in degrees, because these angles are now in degrees. Degrees. And then if we look at what cos of 30 is, it's that number, root 3 over 2 or 0.866. And then on the right-hand side, if we look at cos of 40, cos of 10, plus sine of 40, sine of 10, it's, again, 0.866. So that's good news. We got the same thing. And the next one, 2 cos squared of 40, take 1. It appears to look like this one here, 2 cos squared, take 1. So that just is cos of 2 times that angle. So this is cos of 2 times 40, which is cos of 80. Again, you can double check that on your calculator if you want. This one here, sine over cos, is just tan. So that's tan of 50. And then this one here, 1 over sine 25, is just cosec of 25. Now this next one's a little proof. So cos pi take theta equals minus cos of theta is what we're trying to prove there. And we're going to start from the angle difference formula. So cos of pi take theta. So if we want to line that up, pi would be our A value and theta would be our B value. So that becomes, I'll just write it out. So cos of A, cos of B, take sine plus sine of A, sine of B. So cos of A. All right, so cos of pi, cos of theta, plus sine of pi, sine of theta. Now cos of pi is minus 1, and sine of pi is 0. So this is minus cos of theta, if you like. And there we go. Next one we're going to do is question 6. So it's verifying the double angle formula for cosine works if theta is 40. We want to do this by calculating both sides and check they're the same. So if we're looking at our left-hand side, it's going to be cos of 2 theta, which is cos of 80. And make sure your calculator is in degrees. But if we do cos of 80, we should get this lovely number here, which is 0.174. And we're doing approximately equals sign, approximately equals 0.174. On our right-hand side, we're going to be doing cos squared of 40, take away sine squared of 40, and then we just chuck that straight into the calculator. So cos 40 squared, take sine 40 squared, gives us, hopefully, the same number, 0.174. 0.174. Great. Okay, so that's good. That works. Next thing we're going to be doing is proving our double angle formula for cos. So we're going to start from our sort of addition formula there. So we're going to be doing cos of A plus B equals cos of A, cos of B, take sine of A, sine of B. So that's going to be cos of theta plus theta. So we're going to set A and B to theta. So what we're going to get is cos of theta, take sine of theta, sine of theta. And this is from sort of like your angle sum formula with A equals theta and B equals theta. So really explaining what we're doing here. So that is cos squared of theta, take sine squared of theta, and I reckon we're done. All right, last question we're going to be doing is proving this alternate version of it by starting from what we've got. So I will just start from what we've got. Cos of 2 theta equals cos squared of theta, take sine squared of theta. And this one can be a little bit tricky, but if you look at what we're trying to get, it doesn't have any sines in it. So I want to get rid of that sine somehow. And the way that I'm going to get rid of that is by using a special like fundamental trig identity, which is cos squared of theta plus sine squared of theta equals 1. So if I rearrange that, I get sine squared of theta is 1 take cos squared of theta. And I can actually replace sine squared of theta with 1 take cos squared. So that's exactly what I'm going to do. So that's cos squared of theta take 1 take sine squared of theta. So that would be using this thing here. And then I'm going to be getting cos squared of theta take 1 plus sine. What am I doing? That should be cos squared of theta, shouldn't it? Plus cos squared of theta. And then that becomes 2 lots of cos squared of theta because I have 2 of them. Take 1. Done. And that's our proof for that little bit there. And that is the end of the pretest. So hopefully you found this useful, and please let me know if you have any questions around it.